Hello everybody. This is going to be the next video in the NMR series. I'm doing something a little bit different today. I'm still doing a screen recording, but I'm doing one of my laptop instead of my iPad, so there's not going to be any stylus or whiteboard today. So what I'm going to do is I'm going to rely a lot on screen images of spectra, and also I'm going to use Marvin Sketch to kind of act as scratch paper for us as we go through this. All right, so we finished the four major points of proton NMR spectroscopy the other day, and today I am going to show you how to try to put all those together into forming, a cohesive analysis of a particular spectrum. But first, heck, I need to go through a whole other type of spectroscopy. We haven't done carbon-13 NMR yet, right? So you may be just groaning to yourselves right now, oh Lord, it took all that time to get through proton NMR. Now we got to do a new one. But hey, I got good news for you. We can do carbon-13 NMR in just a few minutes because it is super duper simple. It doesn't tell you as much useful information as proton NMR, but it does give you some useful information that you can a lot of times use as sort of a double check after you've done a proton NMR analysis. All right, so let me go over this with you real quick. Carbon-13 NMR, what it does is, just like with proton NMR, what it looked at was the number of different types of unique hydrogen nuclei. This looks at the number of unique types of carbon-13 nuclei. Carbon-13 is a heavier isotope of carbon-12, which is the one we usually see. All right. And basically, this only tells us two types of information. There's only two types of analysis that we employ with carbon-13 NMR. We look at the number of signals to tell us the number of unique types of carbon within a molecule, and we also can look at chemical shift. All right? There are no integrations to take into account here, so we're not going to be looking at area underneath the curve. We're not getting ratios of carbons causing signals or anything like that. Also, we're not going to have a splitting analysis. Carbon-13 signals, as you can see here in this sample spectrum, they're always singlets. Okay, so there's no reason to worry about spin-spin splitting. So we're only looking at the first two factors. We're looking at number of different signals and chemical shift. And honestly, the same type of factors, or same type of analysis that went into those two factors in proton NMR, they still apply here with carbon-13 NMR as well, right? If you look at a carbon-13 NMR spectrum, the number of signals corresponds to the number of unique types of carbon within the molecule, right? In this example, this is the carbon-13 spectrum of acetic acid, right? You can see acetic acid has two carbons, and these two carbons are definitely non-equivalent, right? They're definitely different from each other, and so you would expect to see two signals, and you do. In this one, we have one propanol, right? And again, you can see we have three unique types of carbon here, here, and here, so you'd expect to see three signals, and you do, right? So for every unique type of carbon in a carbon-13 NMR spectrum, you're going to see a signal. Here's methyl acetate, right? Carbon here, carbon here, carbon here. Three signals are expected. Three signals is what you get. All right? So that's pretty simple. The other thing that you look at is chemical shift, right? And this, again, follows the same guidelines that we learned about in proton NMR. Carbons can be shielded or deshielded depending on what's around them. The same factors that cause deshielding or shielding in hydrogens also cause deshielding or shielding in carbons. All right? So if you have the presence of electronegative atoms, if you have the presence of an aromatic group nearby, a carbon-carbon double bond, carbon-oxygen double bond, those are all deshielding factors, and you would expect the signal to be further downfield. If you have a carbon-carbon triple bond, that can cause shielding effects, and that would be a signal you would expect to find a little bit further upfield. Right. You can find, just like with proton NMR, carbon-13 correlations tables. I don't have one on me at the moment, I don't think, but you can look at it fairly easily. But you can look at the structure and you can make predictions, right? So in this example, acetic acid, this carbon obviously is part of a carbonyl and it's very close to two electronegative oxygens. You would expect this one to be definitely further downfield than the carbon in CH3, and that's what we see. Right? This one is much, much further downfield. You'll also notice that we use a different chemical shift scale. It's usually about 0 to 12 in hydrogen NMR, proton NMR. In carbon-13 NMR, it's usually about 0 to 200 or so. All right. We look at, well, I do have a correlations table. Here you go. If you look at 1-propanol, again, you see signal C here. This carbon is closest to the oxygen, so you would expect it to be a little bit more deshielded than the others. Carbon A is furthest away from the oxygen, so you'd figure this would be furthest upfield, and that's what we see here. Carbon C is further downfield, carbon B is in the middle, carbon A is further upfield. Methyl acetate, carbonyl carbon you'd expect to be way downfield, and it is, carbon B, all right? And then carbon A and carbon C. Carbon C is directly attached to an electronegative oxygen, so it's a little bit further downfield than signal A is. All right, so it's a very, very simple analysis for carbon-13, and like I said, it's in and of itself, it's usually not enough to fully elucidate a structure, but it's a great secondary tool to use with proton NMR and IR spectroscopy in overall analysis. All right, so that being said, we are done with basic background, and now what I want to do is I want to go over some practice problems with you. And I put a couple of resources up on Moodle, a couple of links to different places with good practice problems. This is one that we've done before. We've used this Colorado or Boulder site for IR practice, and we're going to use it again for some NMR practice. And we'll also use the IR as a supplement. Don't think that you have to forget your IR analysis here. IR and NMR are best when they're used together. The more pieces of the puzzle you have to figure out something, the better. All right. So let me show you how we would employ this. Actually, first of all, I totally forgot. I want to introduce you to a mathematical formula that we can use to sort of help us with this. All right, I am Googling something called the index of unsaturation formula. All right, that's going to be a mathematical formula that I'm going to bring up. Oops, that's not the one I wanted. There we go. So let me highlight it here. Write this formula down. You'll find it's tremendously useful, and you can find out a lot about a chemical structure before you even look at a spectrum. All right. This is called degrees of unsaturation. It's also called the index of unsaturation sometimes. It's equal to twice the number of carbons in the molecule plus 2 plus the number of nitrogens in the molecule minus the number of hydrogens minus the number of halogens, all divided by 2. All right. And let me tell you why this is so useful. This gives you a number. All right. This number represents the combined number of rings and pi bonds within your structure. All right. And that gives you a big heads up on what to expect. For instance, if you get an index of 1, that means that you either have a ring or you have a pi bond somewhere, a double bond. If you get an index of 2, that could mean that you have 2 double bonds. It could mean that you have 2 rings. It could mean that you have 1 double bond and 1 ring. Or it could mean that you have 1 triple bond, right? Because remember, 1 triple bond has 2 pi bonds with it. It doesn't tell you exactly how many pi bonds or rings you have. It just tells you the combined number overall. But again, it gives you a tremendous leg up on sort of getting a jump start to the problem. All right. So that being said, let's take a look at some of these practice problems. All right, I have Marvin's sketch here that I'm going to open up to sort of help us along. All right, and I'm going to be sort of switching back and forth between this, so hopefully I don't, give you guys, motion sickness from flipping back and forth so much. I just want you guys to be able to see everything. All right, let's take a look at number one. All right, number one has a formula of C5H10O. All right, so like I said, I'm going to use this in large part just as scratch paper. Please forgive my lack of subscripts at the time. Right this time, I'm just kind of trying to go through it kind of quickly. All right, so that's C5H10O. All right, and then from the formula, we can calculate the index. All right. I'm not going to go through all that either. Hopefully by this time in your careers, you're pretty good at plug and chug. But when all is said and done, the index equals 1. Okay? So that gives us some good information starting off. All right? And so, there's different ways you can approach this. I always like to take a look at the IR initially if I have one. If not, then, I don't use it. But if I have one there, it's a really good way to kick things off. If I look at the IR here, one thing I notice really obviously in this case is that I have this big strong signal at 1716. If you guys remember, that's going to correlate to a carbonyl group. All right, so that tells me I probably have a piece here. Probably tells me I have a carbonyl. And if you'll notice, the presence of a carbonyl would satisfy this index of 1. Okay? So that's going to be sort of a building block I'm going to use as I get into my NMR. All right, so if I'm looking at this, what I'm going to do for these signals is as I read them from left to right, I'm just going to call them A, B, C, and D. Okay, so in this example, we have 4 signals. Starting at the one on 2.4, I'm going to call that A, and I'm going to go right to left, calling them A, B, C, and D. And that's the order I'm going to put things in my Marvin sketch, scratch paper. All right. The first thing I notice here is the ratios. This is a very, very generous NMR spectrum in that not only did they give you integration units to use as the ratios, they actually gave you the exact numbers. It won't always be this easy. Sometimes you'll have to simplify these, but in this case, we don't have to. So I'm going to say that my ratios are going to be 2 to 3 to 2 to 3. That means 2 H's are causing signal A, 3 H's are causing signal B, 2 H's are causing signal C, 3 H's are causing signal D. Forgot the alphabet there for a second. All right. So now let's take a look at some other things. Let's take a look at the splitting patterns, and this can tell you some clues. This is very much like playing detective. If you ever like to play Sherlock Holmes or solve puzzles, this is your thing, because what we do is we find as many little bitty clues and puzzle pieces, and we put them together to find the most logical arrangement. I have to emphasize this, and this can be frustrating about NMR. It's not always perfect. Everything doesn't always match up perfectly. You try to end up with your best educated guess. All right? So let's see what we have here. If we look at this, we're examining signal A. We see that it's caused by 2 H's. And we just got this from our ratios, our integrations. And it's also a triplet. All right, and if you remember what this means, what splitting means, if something has a triplet, that triplet is caused by neighboring hydrogens. All right, so if this signal A is split into a triplet, that means it's next to 2 other hydrogens that are non-equivalent. So I'm going to say it's split by 2 H's that are maybe neighbors or right next door. And if you kind of think about it, you can make some logical assumptions, right? what is the most likely piece or fragment that's going to have two hydrogens that are the same? Probably going to be a CH2 group here, right? That's the most logical case. This is not always. Sometimes you have individual H's that are equivalent, but most of the time if you see two equivalent H's, that means you have CH2, all right? So I'm thinking, I'm going to make a little note here. I'm going to say we might have a CH2 in signal A, and that group might be next to another CH2 since it's split into a triplet. Okay, just a thought, but it's a possibility. All right, then I'm going to look at signal B. All right, signal B is caused by three H's, and that's a singlet. And if you guys remember, if something is a singlet, it is unsplit by anything. All right, and that means it's too far away from anything else to have it split. So I'm thinking this is going to be something that's isolated from other hydrogen-containing species. And if I see a group that has three hydrogens, again, going with the probabilities, I'm thinking I probably have a CH3 group, a methyl group. All right, so I would hypothesize that maybe I have an isolated CH3, meaning that it's not close to anything else that can split it. All right, then if I look at signal C, it's caused by two H's. And if we look at this, it looks to be a sextet. All right, now remember, whenever we have these larger groups, we have to take them with a bit of a grain of salt. Sometimes these larger groups are caused by complex splitting. You remember when we did the splitting trees and I said, well, theoretically you should have 12 peaks, but realistically you might see a jagged sextet or something like that. That all depends on how powerful the spectrometer is. Now what they did here was they sort of magnified the image. I'm going to magnify it some more. And I'm kind of undecided, because you see it's like little tips here. This one looks a little bit split. This one looks a little bit split. So I don't know if this is a regular sextet or if it's caused by complex splitting. So I'm just going to make a note of it. Okay, and if it's complex splitting, either way, it means that it's going to be split basically by 5 hydrogens, right? It's either going to be 5 identical hydrogens causing a smooth sextet, or it's going to be 5 hydrogens that are very, very close in nature to each other that is causing a rough sextet. In that case, it would most likely be a CH2 and CH3. All right, then we look at signal D. Signal D is caused by 3 H's. And we have a triplet. That game means, again, split by 2 H's. So again, you have a CH3 here, most likely. From the integration. And then, maybe that means it's next to a CH2 since it's split into a triplet. Who knows? But that's a pretty good guess, I think. Okay. So if we start putting these together, right, I'm just going to sort of make a chain of 5 carbons here since that's what we have. All right, and so I'm thinking, okay, I have a carbonyl somewhere. All right, and I think I have an isolated CH3. So what I'm going to try here is I'm going to try to just draw a carbonyl at this point, right? And you see here, once I do this, that makes a CH3 on this side, and it's not close enough to anything else with H, so it's not going to split. All right. Trial and error, just like synthesis. You put something down, you put a structure down, and you see, does it fit well with the information that you have? All right. I think I might have a CH2 sequence in there, and that kind of correlates to this part, I think. I have something that might be undergoing complex splitting. I think this group right over here, if you look at here, this is going to be split by both these H's and these H's, and if you total these up, these are 5, so that would probably make a jagged sextet. I think I might have a CH3, CH2 sequence in here, and that would fit well with this part. Okay, so if I'm doing this analysis, then I am pretty happy to say that this seems like a very logical answer. So I would think that this would be 2-pentanol. Unfortunately, you can usually look at the answers, but for some reason the website seems to be having some problems right now. I don't know what. Hopefully they'll fix that. But I'll tell you that that is the answer. That is the answer to this structure. This is 2-pentanol. And so it's very much a process that requires a lot of patience, requiring you to solve little bits at a time, and then sort of put the pieces together in the most logical sequence. By the way, if you're working through these and the website's still not working and you can't get these to show the answers, let me know, and I will be happy to check your analysis for you to see if you're on the right pathway. All right. Okay, so we're going to do another one here. All right. Let's do number 3. Okay. Number 3, this one has a formula of C4H10O Okay, if we do an index analysis here, plugging in, I get an index of 0. So this one should not have any pi bonds or rings in it. That helps out a little bit. And if we look at the IR first, I think we should be able to see a big red flag over here, right? That's that classic alcohol OH signal. So if I'm looking at this, I think I have an alcohol group from that. And that gives us a little bit of information before we even get to our NMR. All right, so if we look at our NMR spectrum, again, I'm going to go right to left to right, A, B, C, D. So if we look at our ratio of hydrogens causing each signal, it's 1 to 2 to 1 to 6. All right. So again, we start sort of making some notes here. A, for signal A, we know it's caused by 1H. And it is unsplit, right? Means that it's not next to anything else that's going to cause splitting. All right, we know that H's on heteroatoms are not involved in splitting, right? So this might be our OH here. It certainly lines up with what we have learned. All right. Signal B is caused by 2 H's. It's split into a doublet. So that means it's split by one other H. Okay. So again, if we see something, a signal caused by 2 H's, usually it's a CH2. And if it's split into a doublet, we think it's split by one other H. So we might have a sequence in there of CH2CH. All right, signal C. All right, it's caused by one H. And it is actually split into 1, 2, 3, 4, 5, 6, 7. It's split into a septet. So again, you have to keep in mind possible complex splitting. Maybe, maybe not. Or it may be split by 6 equivalent hydrogens. Who knows? All right, and then signal D. Signal D is caused by 6 H's. I really should capitalize all my H's. Sorry about that. All right, and that is a doublet. Okay, so if I see that we do have a signal caused by 6 H's, that's going to tell me back in signal C that probably it's not going to be complex splitting, and it is split by 6 equivalent H's. All right, and if these 6 H's are split into a doublet, that means I probably have a sequence where I have one hydrogen, not what I meant to do, sorry about that. I'm just going to put an R group over here. But I think this could be a sequence where you have a CH next to 2 equivalent CH3s. If you think about it, what's the most likely thing that's going to have 6 equivalent H's? It's going to be something that has 2 CH3 groups. All right. So we have a bunch of clues here. All right. So let's start putting something together. All right. You'll notice the fact that the most deshielded, the most deshielded signal is the singlet with one H. That would correspond pretty well to the OH signal, so I think that's good. All right, and the next one furthest downfield is a 2 hydrogen unit. So that's going to be probably, I think, an OH next to a CH2. And since this CH2 is split into a doublet, I think the next one is probably going to be a CH. Whoops. And we thought we had that CH group next to the CH2, which we do, and also next to 2 methyls. So this would be my best guess after analysis, and I can tell you, in fact, that this is the answer. This is the correct answer for this one. All right, let's try another one. Let's try number 5. All right, so number 5, we have a formula of C4H8O2. All right, once we do our index calculations, I got an index of 1. So again, we're going to have 1 ring or 1 pi bond. All right, if I'm looking at the IR analysis here, again, I see straight up right away we have a carbonyl group, and this is going to be what's going to account for our index of 1, right? I also see some strong signaling in here, all right? These two signals are going to be important because if you look at your IR notes, this indicates the presence of a C single bond O, right? We have a CO single bonds are in the fingerprint region. They're signified by two peaks, one, both of them between 1300 and 1000, and we see that here. So what I get from the IR analysis is that I think we have an ester group. And that means we're going to have this. Let it go where I want it to. Sorry. There we go. There we go. Okay. So I think we have this fragment in here. And that tells us a lot. That takes care of 2 of our carbons and both of our oxygens before we even get to our NMR. All right. Again, going left to right, ABC, we have a ratio of 3 to 2 to 3. Okay. So looking at signal A, it's caused by 3 H's, right? Probably going to be a methyl group if it's 3 H's, and it's a singlet. So my best guess would be that it's an isolated methyl group. All right, signal B is caused by 2 H's, and it looks like it's a quartet. So it's probably split by something with 3 H's, which would probably be a methyl group. So this tells me I probably have a CH2 CH3 sequence in there somewhere. Signal C is caused by 3 H's. Again, that probably means a methyl group. And it's split into a triplet, which means it's split by something that has 2 H's. So this, again, lends credence that you probably have that CH2 CH3 sequence in there somewhere. Okay. All right. We see that also this group right here is furthest downfield. All right. So that means that CH3 group is probably going to be pretty darn close to the carbonyl. All right, since it's so far downfield. So putting all these pieces together, I could come up with something reasonable that looks something like this, I think. And this one actually, I think, would have a couple of acceptable answers. Here's one of them. Okay. Definitely an ester. So here's our isolated CH3 that's far downfield. All right. The next one, furthest one downfield, is CH2. And it's fairly close to this other oxygen. and the furthest one upfield is a CH3, which would correspond to that. All the splitting patterns work out pretty well, so I think this is the most likely structure. There is one other structure that's fairly similar that could be it, but I think the chemical shift really favors this one. I can't check it, unfortunately, because the button's not working, but this would be a very logical analysis. All right, let me do one more, because I know I'm kind of droning on here. Let's look at number 12. That's a good one. Number 12 has a formula of C7H9N. All right. Now this one is going to be much different as far as the index goes. Once you plug everything into the index here, you should get an index of 4. So that means it has some sort of combination of rings and pi bonds that equals 4. So that's pretty interesting. Okay. All right. If we look for quick and easy stuff to get from our IR, if I'm looking at the IR, I'm definitely seeing this right over here. This is sort of a moderate peak, a pair of peaks at the sort of the 3,300, 3,400 region, right? And that really is in close agreement with what we see with primary amines. So I'm going to look for the possibility of a primary amine here. Also, I can see some stuff here. This looks like, some sp2ch stretching. And I see some strong peaks down here. These look like OOP bands to me. And what has OOP bands? Aromatics. So I'm thinking this one might also be aromatic. All right, just a couple of things to maybe look out for and see if we can see in our NMR. All right, so here in this one, we actually have 4 different signals, but 2 of them are sort of having been trouble read individually by the machine as far as the integrations go. So this one sort of collectively took these 2 signals down here as 4 hydrogens. So I'm going to count them together. Say 4, 2, 2, 2, 3. Okay. Now, signal 4, or excuse me, the signal A is found in a very unique part of the chemical shift spectrum. It's found from about 6.5 to just a little bit over 7. Anytime you see a cluster of signals in a chemical shift range of about 6.5 to 8, that usually indicates aromatic H's. All right? That means H's directly attached to aromatic rings. All right? A lot of times, not always, but a lot of times the machine will have trouble individualizing different types of aromatics on a particular ring. So sometimes it just lumps them all together, and that's what happened here. All right, so this tells you that you have an aromatic ring with 4 hydrogens. And if we think about it, if we have 4 hydrogens, that means that 2 of these carbons must have something on them. So this is going to be a di-substituted carbon. Excuse me, di-substituted aromatic ring. All right, so that tells us a lot. All right. Signal B caused by 2 H's. And it is sort of a little bubble. It's a little blip. That's a broad singlet. unsplit. All right. To me, that really correlates very, very well with the primary amine hypothesis, right? Because remember, H's on nitrogens are not involved in splitting. So I'm thinking that tells me I have an NH2. And then signal C is caused by 3 H's, and it's a singlet. Again, meaning it's unsplit. Right? So a 3 H's usually means CH3. So that's telling me I probably have a methyl group that's isolated. All right? So in essence, this is pretty simple. You can see here we have an aromatic ring. It's disubstituted. One of the substituents is going to be NH2. One of them is going to be CH3. All right? The only thing that we don't know is what substitution pattern they'll have. Will they be ortho, meta, or para? Well, if you look over here back at the IR, the OOP bands correlate to the meta disubstituted. We have 2 major OOP bands here, one of them at 775 and one 690. If you go back to the IR notes and you look at the primary indications for ortho, meta, or para, that matches up very nicely with the meta disubstitution. So, whoops, sorry about that. So, this is going to, whoops, no, darn it. That is going to be the correct answer for problem 12. Okay, so I could do more, but you're probably getting bored by now, so I'm going to stop. That is the process that you need to go about. It's a bit of a tedious process, I'm not going to lie. It's not perfect. Not everything always agrees, like a puzzle piece, but you come up with your best guess based on the best pieces that you can put together. These are some really good practice problems on here. Again, unfortunately, it seems like they're having problems and you can't see the answers. If you need me to tell you the answers, I can tell you whether you're doing it right or not. I also put a link up to another site, the Web Spectra site. And so if you click on that link, you're taken to this page. Again, this provides you a whole bunch of very good problems here, split up in beginning, intermediate, advanced. You're definitely not ready for advanced yet. You might be able to get some of the intermediate ones, hopefully. Sorry, I have the hiccups. Some of these have different things, like, if you look at this one, for example, this got the formula, the proton NMR, and the carbon-13 NMR, which is nice, but it doesn't have the IR. And that's fine. You can still solve them. Some of them, the ones with yellow dots, they do have the IR. So use any thing at your disposal with these. Couple of things I want to mention is that if you use these, I click on the NMR, number one, these do not have integration units, they just have the lines. So you remember in one of the previous videos I told you what to do if you just had the lines, right? So you'll need to do that. Also, you don't see much detail here, but you can click on these, and if you click on a given signal, it'll give you a magnification. So now you can see very nicely that this is a quartet. Click on the zoom out button, you click on this one, we got a singlet, and this one we have a triplet, right? So be sure to zoom in and out as appropriate. And also, if you look at the carbon-13 NMR, you can see how, you can double check and see how these match up. In all of these, you're going to see a darker signal here, right about, I don't know, 78, 77 or so. This is a solvent peak. You will ignore this one, but you go with these other skinny peaks, right? So this gives you 1, 2, 3, 4 different carbon signals. That means we have 4 individual types of carbon in this structure. And these do have working answer keys on them. So we look at it, boom, here's the answer. 4 different types of carbon. So be proactive in working these. I am very shortly going to put up a set of homework problems for you guys to work on. And there will be at least a problem or two related to NMR on the final exam. All right. Along the way, if you have any questions or problems, please do not hesitate to let me know. This is, this is one of the more difficult aspects of OCHEM, so be patient with it. But as long as you're patient with it, it should come. All right. All right. So that's all for now. Until next time, I'll talk to you later.